Well, hello and welcome to Simulate Building Performance. My name is Dr. Nagman Khan. Delighted to be joined by my colleague, Senior Application Engineer at Simscale, Darren Lynch. I'd like to welcome you all to this webinar by Simscale. It's a super interesting topic. Before we jump into that, let me just quickly introduce Simscale. So Simscale is a cloud-native simulation platform. That means you can access it via a web browser at any time from any place and is fully hosted on the cloud. And our aim is to make simulation accessible at any scale and deliver the best-in-class simulation capabilities for architects and engineers. Now, why are we here today? We're looking at the topic of building performance. Now, many of you might have joined previous webinars where we've talked about specific features and capabilities when it comes to simulating buildings and cities. Today, we want to give an overview of all the capabilities that are available, ranging from microclimate, thermal comfort, fabric energy efficiency, and indoor air quality. Okay, using a single CAD model in one platform, you can see how you can use one platform and one model to do many types of analysis. Okay. Now, we need this complex building physics. We need to capture it to design more and more advanced buildings that can help us meet our strict targets towards net zero. And the kind of things you can do very quickly and get started, including external wind comfort and safety, thermal comfort and overheating, ventilation and air quality, and solar gains and fabric energy efficiency. Very quickly, we have some fantastic resources on our website. For example, the microclimate simulation for urban design white paper. Please do take a look, and we'll send the links to these in the follow-up email. It talks about these topics, including building aerodynamics, wind comfort, outdoor comfort, modeling trees and vegetation. Some examples you can see here on the bottom right and the top right, natural ventilation strategies, site sustainability, and more. And looking more at the indoor environment, again, we have another new white paper that's been released. A ton of different types of analysis you can do at the room level and the sub-room level, even looking at HVAC units, air handling units, pumps, fans, ventilation flow, and things like room air temperatures, occupant comfort, building envelope heat transfer, thermal bridging, and examples such as calculating CO2, air quality, data center cooling, window opening strategies, and many more. Now, I'll let my colleague Darren Lynch explain a bit more about how we do this. Thank you.
Hello and welcome to today's topic on simulating building performance. And internally we dubbed this project One Building to Rule Them All, because really what we wanted to do is present a design scenario in which we were interested in both the indoor comfort and air quality of a room, but also interested in understanding its outdoors environment in terms of wind comfort, but also how well a natural ventilation scenario would actually perform on this building within a deep, complicated urban environment. Firstly, let me introduce you a little bit to the demo that I'm going to be performing. So the purpose of this demo is really to introduce you to the Simscale platform to understand what the workflows look like. But we really want to give you some context as to what we're looking at as well. So today we're going to be looking at a external building aerodynamics simulation. It is part of the one building scenario that we looked at just a minute ago. And what we aim to do is to understand the flow around the building due to its design, but also the influence from the surrounding urban environment. You can actually see a very large shopping centre here that is going to be very influential to some of these results that we're going to be seeing. We're going to be looking at a low-rise building. So this is a new building just located here. I'll talk to you a little bit more about it later. But what we're trying to understand is how comfortable people are around the urban area surrounding this new building, but also what the pressure coefficients look like on their facades and how this is likely to influence the natural ventilation of the commercial room that we'll be discussing as well. Hi, and welcome to the Simscale platform. So Simscale is, of course, a cloud-native simulation tool. It requires you to have installed no local software. It requires no local hardware to actually solve the simulations. And you access the Simscale platform via a web browser with username and password. Simscale, of course, offers real-time support, allowing you to connect to our experts and get advice on anything you're trying to do, or just pointing out resources that you are needing to get hold of. There is also easy collaboration, so if you wanted to work with your colleagues or share results with your clients, then of course this can be done just by inputting their email addresses or usernames and giving the appropriate permissions. Now, in terms of the user experience, the Simscale platform has this large viewer space in the middle, where typically this is where you're going to be visualizing results. Also could be where you make graphical assignments and also look at geometries that you've uploaded. On the left hand side, this is what we call the simulation tree. So as an end user, we're going to be uploading geometries here. We're going to be setting up the simulation, inputting various parameters into the simulation setup. So the topic we're looking at today is the one model to rule them all, where we're trying to assess different AEC topics all within one kind of environment. And as I mentioned in the lead up here, that we're going to be looking at mainly the external building aerodynamics side of things in this platform demo. So the kind of things that you can get out of these simulations, I'm going to talk about them a bit more in detail in the presentation slides afterwards, but the main things you can get out of these simulations are pressure coefficients on the surfaces of the building, on the facade, so we can actually assess what the opening pressures are going to be like. We can also have a look at what the pressure values or the wind speed results around the building look like, so we can kind of see from a top-down view how the flow is interacting with the building. So, for example, you've got some high pressures here, low pressures here, some moderate low pressures behind the building as well over here. And if we wanted to change this to, for example, wind speed, then we can absolutely just change that field over and start having a look at cornering effects, etc. Additionally, what we can get from these simulations is the pedestrian wind comfort. So the final piece to this big puzzle might be, okay, so we can improve the natural ventilation of a room. We can see what the pressure coefficients are like. We can see what the flow patterns around a building look like. But is a person actually comfortable moving around the building itself? And of course, I'll talk about the what these results actually mean in the following slides. So we briefly had a look at what the results we could actually obtain from these simulations look like. At the moment, we're on a zoomed out version of the Lawson criteria. But how easy is it for us to really obtain some of these results? You know, we want to be using this at a fairly early stage in the design process. We want to be using this to gain understanding as to how we could improve the design iteratively. So we don't really want to be spending a lot of time here setting up a simulation that could take days or weeks. Rather, we want something that's quick and simple to do, probably in the space of no more than an hour or two. So, to start this process off, what we would do is we would upload a geometry to the Simscale platform. So we can actually press the little plus button here, drag and drop it into this space, or find it on your computer. What I'd recommend is use the STL file format, which is applicable both to Revit, Rhino, and also SketchUp as well. So that is a perfect file format for either of those three options. And once you've drag and dropped it into this space, you will see, of course, it uploaded to the Simscale platform, and you can inspect it to make sure that it is representative of what you're trying to simulate. Now, when you're ready to start setting up a simulation, you can come along to the simulations, press the little plus button, and of course press pedestrian wind comfort. Now, this is highly automated. You're not having to do a lot here. There's 3 simple steps that we ask you to perform, and that's going to give you a simulation that's just ready to be solved. So the first step is to actually come to the region of interest. It's as simple as defining a radius and a center point. So this is really your site plus a bit. Which bit are you actually interested in? This whole urban environment that you've actually uploaded to the Simscale platform. Once you're happy with that, you can save that, move along to wind conditions, and this is actually located in Nottingham. So I'm just going to type in Nottingham for my input, and then I've got 2 options. I can either upload my own wind data, or I can import the wind data from our connected service Meteor Blue. And here we can choose the number of wind directions that we wish to save. As I said, this is a little bit in the earlier stage of design, so we're going to go for 6 or 8 wind directions here. And we can also change the exposure categories as well. What that actually means is what the wind actually looks like coming into the environment. So if, for example, to the north, we're in dense urban area, then we can of course select that, and we would go around the clock selecting these. And once we're happy with that, we can press save. Now, the next step is to actually export some results. So tell the Simscale platform what we want to get out of this. The first thing we want to do is, of course, add a pedestrian comfort map, because we want to know how comfortable people are in that environment. And I'm going to select the ground absolute, which means the bottom of the wind tunnel is going to be offset perfectly by 1.5 metre on a planar basis. And we can save that. Next up, what I want to do is output pressure coefficients. So I want to output those pressure coefficients on the building facades here. So what I'm going to do is come along to additional result export, statistic result averaging, and I'm going to box select the main building that I'm interested in right there. Select external surface fields, and these get added to the assigned faces. And when we're happy with that selection, we can press save. Now at this point we could iterate the mesh settings, but I'm going to quickly move through this for this demo. I can press the start new simulation run, and it gives me an estimation as to how long it thinks it's going to take, how many compute resources it's going to consume, and also what the minimum cell size is that you could of course iterate at this stage as well. And when you're happy to start simulation, you can hit start. Now it's important to note here that you could run as many simulations as you like at once, so we're already anyways running all wind directions in parallel, but if you had 5 different design scenarios that you want to test, then of course you can test all of those at once as well. And when you're happy to start simulation, hit start, and you'll actually get an email when it's finished to say come back and check the results. And it's there that we started the demo with some of the typical results that you will get out of that simulation. So we've come full circle. So let's go back to the slide deck and discuss exactly in detail what we saw in terms of results. So firstly, we're going to look at pedestrian wind comfort. So that was the last result that I showed in the demo. Naturally, I'm doing it in reverse order. So wind comfort is typically an annual kind of output that we get from the Simscale platform. We can split it into seasonal, but what it represents is the different activities that people would be comfortable doing in different areas, as I mentioned. I've given a few different examples of where uncomfortable might exist, and for example it's this cornering effect where it's also compounded with a bit of channeling there. There's pedestrian walking effect and activity, and also business walking over here that you can see. And what we really want to do is we want to make sure that the activities that we expect pedestrians to be doing around our site are going to be suitable for the activities that would be deemed comfortable to perform at that site. So we're really comparing our expectation with the comfort results that we're receiving from the Simscale platform, and that's exactly what we're doing here. Pedestrian comfort is really good for telling us where people are comfortable, if they are comfortable for doing the activities we expect them to be doing, but what it's not that great at is telling us why they wouldn't be comfortable doing that activity. So although we said in the demo that our comfort criteria was actually quite nice within the space that we're trying to develop on, this isn't about my project, this is about your projects. So it's not always going to be the case that they're comfortable, and what we can actually look for is several different effects to actually allow us to improve the results. And these effects might be downwash, for example. If you've got taller buildings, this is going to be incredibly relevant to you. Cornering effect, sharp edges are always going to cause a speed up around the corner and impact the comfort within that space, and also the channeling effect. So if you've got buildings that are close together and you're expecting people to do some less strenuous activities between them, then of course something needs to give. You need to try and mitigate that somehow. So we can use these additional results, wind speed results, these streamlined results, all from the same simulation, to help us understand that comfort plot and help us make these design decisions at an early stage. Now, with comfort aside, what else could we obtain at an early stage? Well, if we wanted to be designing a natural ventilation scenario, then we could also look at pressure coefficients, or average pressure coefficients. And I showed you these kind of results within the Simscale platform. Now, when pressure coefficients are usually used as inputs for simulations that employ a natural convection as a cooling strategy. So this could be a co-simulation process in thermal modelling tools, or it could be another CFD simulation to actually understand what the flow within a building floor looks like, for example. Now, we can obtain these pressure coefficients at all of our openings through advanced CFD like this, or wind tunnel testing, so depending on what you've got available to you. At an early stage, it doesn't really make much sense to be doing wind tunnel testing, so CFD does tend to be the preferred method, certainly in early stage areas. And this becomes more and more relevant with the more and more complexity in the context and the surrounding topology. And what I really try to highlight here is that this large shopping mall really does give us some results that we would otherwise expect to be strange. So just because a building is 10 meters tall and it has a window at 2 meters, at 8 meters, etc., doesn't mean to say that they're going to have a pressure coefficient of 1 on that windward facade. Actually, if it's in deep shielding like this case is, then we're not going to get pressure coefficient values anywhere near that. And we need to make sure that we understand that is going to influence very heavily the performance of a natural ventilation strategy. So with that said, what kind of insights can we get out of pressure coefficient values? Well, we can start to look at pressure coefficients around the building and start building a picture in our head what flow paths the wind or the air is going to take within the building, and what we can do about the indoor building layout to either slow wind down or allow wind to naturally ventilate more, depending on the scenarios that you're trying to simulate. So for example, if you wanted a higher refresh rate, then naturally you're going to want to encourage a faster flow. But if it's a cold environment, then perhaps you want to limit the amount of breeze going through a floor. And this is quite visible. So wind or air will naturally travel from a high pressure region to a low pressure region. So we can use that to our advantage to really understand what certain scenarios would look like. So for single-sided ventilation, if you imagine this was a closed off room, then we would get single-sided ventilation travelling from this opening to this opening. For cross ventilation, if you imagine there was only an opening here, and that was either some kind of room or there was some sort of flow path going from A to B, or the front to the back, then it would travel straight through that building, where this would be the low pressure region and this would act as the high pressure region. So it forced that cross flow ventilation. And finally, stack ventilation. Now this is going to be, of course, enhanced by the buoyancy effect, but in this case, you can actually see that there's a higher pressure at the bottom of the building, lower pressure at the top, due to complicated flow patterns around that building, and therefore it's going to add to that stack effect even more. So we haven't even done an indoor simulation. We're already able to pretty much gauge what we could do to actually control the natural ventilation within our building. But of course, we will also have a look at an indoor case in a minute as well. Finally, what sort of effects can we be wary of, essentially, when doing these natural ventilation strategies? So we should be wary of the cornering effect. As I mentioned, this can heavily influence the single-sided ventilation scenario, where you can actually see, although not a huge pressure difference, we are going to get some single-sided ventilation here where you might not expect it. Wind shielding, as I mentioned, this is a huge area of shielded urban landscape that's been generated by this shopping mall. And you can see all this, these fluctuations, these low speed areas, where the building of interest, actually that one in the middle, is completely within this this recirculation low speed zone. And that is going to reduce the amount of flow or flow potential through our room. And finally, the channeling effect. Naturally, any higher speed flow is going to put pressure on the buildings when it comes to an abrupt change in direction. So we've actually got a compound channeling effect here, where the flow actually hits the windward facade, or the local windward facade of this building here, and generates a high pressure region as it turns away from its regular path. And this additional pressure is of course going to create a high pressure zone, and it could heavily influence also the natural ventilation due to that. And this is sometimes very, very hard to figure out without a CFD study. In fact, most of these effects are going to be very hard for you to figure out, especially when it's behind such a shielded area. Good. So that concludes the external side of things, and perhaps it gives you a good idea as to what early stage design decisions you can make based upon a very simple simulation setup. But let's quickly look at how we could also use those results to further understand the indoor space. So as I mentioned, maybe we had a floor plan layout that we wanted to try, or a ventilation strategy that we needed to assess. We can bring those pressure coefficient values in to be incorporated to a boundary condition within an indoor comfort and air quality type simulation. And here are some outputs that you can get from that. So on the top here you're seeing the scenario that we've simulated. As you can see, it perfectly fits in with the building that we've just been looking at. And what we've done here is we've simulated a forced ventilation strategy, but also a natural ventilation strategy, just so we can understand what the pros and cons of both. And what we've actually output is many different quantities such as temperature, airspeed and air direction, but also thermal comfort parameters such as PMV and PPD. Now additionally, we've also looked at the age of air. So this is like a air quality metric. We don't want air to be too old or too stagnant within our space. We want it to be actually quite fresh and quite clean. So that's why that is important. But also we can look at CO2 concentrations as well within the space. So that concludes our short presentation using the one model to rule them all showcase. Please, if you've got any questions, feel free to start typing them. We're going to be going through them in just a minute.